So what exactly is OpenOCD, if the next slide actually works? So we are going to cover a few topics here. We're going to talk in terms of, give a brief background on what OpenOCD is, what kind of features it supports. We will go through some of the hardware setup that is needed. Different boards have different setups. We will go through some basics of building OpenOCD. There are different techniques of installing OpenOCD on your system, and how it integrates with IDE. Now, if things go right, we might be able to integrate this with VS Code, but let's see. We will look at two different ways of debugging. One is to debug the U-Boot, which is typically what we do. Another will be to debug Linux kernel. If we have time, and I couldn't get that set up right yet, we will try and look at self-hosted debug, which is the other stuff that we have to do. Now, most of you folks have used JTAG tools of some sort, right? CCS. A lot of folks in TI tend to use CCS. Many of the folks have used Lauterbach as well. OpenOCD is such a similar solution. It's an open source solution, and it provides capability for doing JTAG debugging on various devices. It has support all the way from microcontrollers to high-end processors that we have as well. As of today, most of K3 devices are supported in OpenOCD, or they are on track to getting merged. In terms of features that OpenOCD provides, the way that we position OpenOCD is your cheapest of all the options that are available. It is also probably the widest supported option from an open source community perspective. It is limited from some perspectives, but then you get this essentially for free. Positioning CCS will be somewhere above this. OpenOCD is your basic debug. You can literally get like 80% of your debug stuff solved in OpenOCD. CCS gives you tracing capability, some of the configuration files and gel files that we usually create, right? That kind of support, which is essentially DSS scripting capability. On top of that, positioning would be what we would call high-end debug tools like Lauterbach, etc. So long story short, OpenOCD is your entry-level debug tool. How this looks like on the actual hardware. So the first thing you'll probably have to do is connect, how do I connect OpenOCD to the system? But before we go here, there is a lot of documentation that we have written in U-Boot documentation in upstream itself. Overall, you use some sort of an IDE tool which interfaces with GNU debugger, which in turn talks with OpenOCD over a network interface. So you could literally have OpenOCD running on your PC in Dallas, and the actual GDB instance could be running from India, and they would communicate over TCP protocol. And you could have an IDE hosted on your desktop in India, for example. So there are many combinations that you can create out of it. You then have some sort of an interface. This could be over XDS 110 or what I like to call as Tampa, which is a JTAG adapter. Like for folks who are familiar with XDS 560, etc. Tampa is such a solution, but you can get it for like 30-40 bucks. And some sort of interface cable that connects to the SoC itself. Within the SoC, we have debug SS, which orchestrates the entire debug of the entire SoC. So you have interfaces going to Cortex-R and Cortex-A, and we will show debug of Cortex-A as an example, but Cortex-R is equally easy to do. So going back, in general, there are three groups of hardware interfacing that we have seen across the K3 platforms. Most of the boards do have what we call as an XDS 110, this little chip sitting on the board. So all you need is a micro USB cable. You plug it in and boom, you're up and running, ready to go. In which case, all you care about is your OpenOCD installation on your PC and a micro USB cable that you connect to your board. The other set of boards are, I think AM68SK is a good example. TDA4VMSK would be the other example, if I remember right. Both of these boards, due to the form factor of the board, we couldn't put an XDS 110 on board itself. Instead, what we provide is a CTI20 pinout. And you need some sort of a cable to interface and an adapter to interface with this. So I put some links here. Again, this is available in the U-Boot documentation. I put a link over here as well. So there are certain dongles that you can buy, like the Tampa dongle, which provides an ARM20 cable. So this you can, again, there are links for you to purchase them. And then you have the CTI20 to ARM20 adapter. Now, this is a little hard to procure. There are a few options like the Sega site, which is probably the best that I've seen so far, that you can purchase this adapter for around $80 or so. Lauterback also provides it, but I think Lauterback adapter cost is around $100 to $200. Now, if you do have a PCB manufacturing capability, the BeagleBone guys had used TI20 previously in BeagleBone. So there are some open source design files that are available that you can provide to a PCB manufacturer to manufacture these boards. And there is JCB PCB or JPCB. There are a few websites that you can give your design files and they'll manufacture the board, put the headers on it, and they'll ship you an assembled board back. I haven't tried it. Instead, the way that I went was to buy the Lauterback adapter. There used to be another company called Tin Can Tools that used to provide a similar adapter for $20. And that was the best I've seen. But they are no longer in production. So I'm not providing you that link. The third interface, which you typically see on the newer K3-based Beagle devices, is Tag Connect. Tag Connect is a proprietary cable interface. The big difference on this system is that on the board, all you have is the JTAG pads itself. So you don't have connectors sticking out of the board. The connector comes from the cable, and it is like a power pin. And you just plug it onto your PCB. So it's a cost reduction mechanism that Beagle guys have adopted. And I think a few other companies also seems to have adapted the standard. In which case, you had to buy this expensive cable. Again, it's around $40-ish for this cable. This adapter is another $20-30. So around 90-ish bucks of cable that you'll have to buy. And Tampa remains the same. So depending on the board that you have, you essentially have to get some hardware setup done. Now, this is typically the TI boards that we have seen. Now, customer boards may come with something similar too. Many of the customer boards may have standard ARM connectors on them, or some may have the TI standard CTI20 as well. Depending on which way your customer platform is, you'll have to pick and choose the cable combination though. Okay, now that you have the cable, you have the hardware debug module. The next step for you would be to set up OpenOCD. Now, depending on your distribution, if you have a standard Linux distribution, OpenOCD might already be present on the platform by the distribution package manager. They typically tend to provide a stable version of OpenOCD. You would probably have to consider updating OpenOCD for newer platforms. There are a few nuances involved, but overall, the build procedure is very straightforward. You have a set of dependency packages that you need to install. And these are like standard stuff, libusb, package config, etc. You can download from the mainline U-Boot, OpenOCD, and git submodule bootstrap configure and make. The last step is actually nice to do, but if you don't have sudo permissions, You can probably get by at this stage as long as you have UDEV rules that are installed. And we'll come into that concept a little. So just a quick show. Meanwhile, so this is on the bottom left is my OpenOCD folder. So if you do, let me do a get team -50x./bootstrap. It's rather fast. So when running through them. And in case you have any packages that are missing, the .configure will report it to you and you have to install that package. But the list that I provided typically is sufficient for you to run it on a 2204 or any of the Debian variants. If you have a Red Hat based packages, you'll have a slightly different package manager that you'll have to use. And there we are. It's all built. Now the find dot minus iname star dot rules. So you'll see some UDEV rules that are available within OpenOCD. So all you need is this UDEV rules installed on your PC. That's essentially what you need. And once you do that and you UDEV admin reload the control these rules in, you can just plug in your USB cable and the rules will ensure that the user has permissions to access OpenOCD. In my case, I've already done it, but if you would like to do it, you can do /etc udev rules.d, copy this in sudo udev admin control -- reload rules. Again, all these steps that I'm just mentioning is also documented in OpenOCD documentation. Sorry, U-Boot documentation, my bad. So we have tried to keep the U-Boot documentation detailed enough for you to follow these steps, and you have almost all instructions that you need here. Now, that's it. Back to our slides. This is the basic build itself. Once you're built, you have many options of IDE integration, all the way from VS Code to, and I'll try and showcase how VS Code integration works. Remember, VS Code was designed as an editor. It wasn't meant as an IDE. But people have figured out how to make VS Code an IDE too. And many people are using it from that perspective. So it is capable of doing a lot of things. But my favorite has been GDB dashboard, which is usually the place that I usually go to. Now you can do debugging with native GDB as well. No problem. That'll work too. Or you can use quite a few other IDE integration. The other one that I usually go to is Lauterbach. Lauterbach also has a GDB interface. And Lauterbach has an IDE. People usually think that Lauterbach is a hardware. Usually they have two solutions. They have the hardware interface and they have the IDE interface as well, which is another place that I usually go to. And I prefer using that because it's a familiar environment for me personally. But for the sake of this presentation, I'll stay away from that. Let's see if we have time, we can probably go there. The interface itself is very straightforward. If you go into the U-Boot documentation, I've kind of given a list of various IDE interface solutions that you could probably go with. Now, connecting to the board itself, it is rather straightforward. Now, in my case here, I have built the very latest U-Boot source code with the latest TFA, Opti, etc., and it is staying at shell at this point. Now, what you can't see is me connecting the USB cable to the board, which is connected. So I have a little screenshot for you guys to see that. This is how my setup is looking right now. So there's XDS 110 that is connected to the PC. The console is also connected to the PC and the power supply is on. I'm using AM625 as an example. But depending on which SK EVM that you're on, there's documentation around that too. So the way to start this up is if I'm in the TCL folder, /OpenOCD -F, board TI AM625 evm.cfg. Boom. That's it. Now I have OpenOCD running and it is ready to talk to any of the processors. This log is very important and you can control which network port it can open to. I have given support for almost all the standard processors. The ones that I have not supported at this point is C7X and C6X. Unfortunately, that information is not public domain, so I cannot quote unquote open source it. So if you're working on C7 or C6, DSP solutions that TI has, you will have to work with the higher end debug tools. Both CCS, Lauterbach do have support for that. So you'll probably have to switch over to that. If you're on the ARM cores, it's much easier. So this system controller is what we call as DMSC or SMS. That typically is your M3 or M4F, which runs TIFS. On GP devices, you can actually access this over JTAG. On high secure devices, both HSFS and HSSE devices, this is not available by default. You need a special key that TI provides to give access to this. And the reason for that is that the security controller actually has access to a lot of TI secrets, which we wouldn't want people to look at because we have all the firewall protection preventing access and you don't want to get through JTAG to see it. So fortunately for us, I'm using a GP device right now. So we can actually get inside it if we choose to go. The interesting part of this is that the port number, this network port on my local host, if I attach to this port, it is actually talking to the TIFS control, the TIFS processor. If I talk to the port 334X, I'm actually talking to A53 and so on. Now, you would obviously ask me the obvious question saying that I've got 4 A53 processors. At this boot stage in U-Boot, at this stage, only one of the processors is started up, not all the other processors. So what if I wanted to debug in SMP mode, like all the processors running together? And there is a way to do that too. And we'll address it at that point. This AM main 0R5, in the case of AM625, is the boot processor. So for our example right now, since A53 U-Boot is up, R5 is actually running the device manager processor. You also see something called as a GP MCU. This is the M4F sitting on the MCU island. Typically, we would run FreeRTOS or AutoSAR or something of that form there. So you can actually debug all these processes simultaneously, which is another cool thing about OpenOCD. Because they are network ports, you could locally debug A53, while your colleague in India is debugging the same board for the M4. Another colleague is debugging the R5. And if you like, yet another colleague debugging the TIFS core. So this gives you flexibility of, literally distributed debug. Now, most of us typically wouldn't use that. It is only when you hit this unique debug situation where you need multiple developers getting involved. It's only in that case that you need to do it. There is no security control. Keep that in mind. So if you were to run your board on the internet, for example, and you were to expose this network board, there's no protection scheme in place. However, you can put a SSH tunnel in the backend. That way, the OpenOCD runs on your local ports, but the access to that is over a SSH tunnel, and your SSH key can provide you the protection. So there are different ways of skinning this, depending on how you like to do it. Anyway, So back to our slides. So this is essentially the setup that I have. We spoke about starting up OpenOCD and what those ports look like, which we just saw here. And what do these network ports really mean? And this will vary depending on the SoC, the microcontrollers that you have. This list will vary dramatically. On an AM69 or a J784S4, the TDA4VH processors, this list will be massive because you've got 8 A72s and a large number of R5s on the system. Depending on that list, it will tell you exactly which processor is on which port. And if you don't like this port, for example, you have OpenOCD options for you to change the network ports as well. Now, that said, there are 2 additional network ports that are of interest too. Port number 444 and 666. These 2 network ports allow for automation. So you can do a local telnet to 444 and directly talk with OpenOCD without using GDB. For example, there is something called as memory AP port. You don't need any of these processes to look at the SoC memory. So Debug SS has a port directly into the SoC fabric. So you use the mem AP port and you can dump registers, look at DDR content, even without touching a single processor. Now, that is very useful when your processor has crashed for some reason and is not accessible, or maybe the processor has not even started up. The third case that you could have is that the processor is in, let's say, low power mode. For example, you're debugging deep sleep path and you don't have access to the processors because you're going down the last stage sequences. So you can use the mem AP port to get inside the SoC from the debug subsystem and look at various peripheral control MMR, PLL registers, I don't know, DDR controller registers, or whatever that you would like to debug. Another place this is useful is when you are debugging the memory MMU tables. For example, R5 has something called as RAT, which is essentially an address map table, which is kind of cheap because R5 by default doesn't have an MMU. So your physical address table, which is in the 64 address space, now needs to be mapped to a 32-bit address space. So we use RAT to do that remapping for the R5 processor. We do the same for M4 as well. Now, maybe you configured it wrong and you have an issue where you think you're writing to a GPIO, but that GPIO is not behaving the way you expected it to. And you are now suspecting that maybe my RAT configuration is wrong. Is the GPIO really programmed? So you can come from the debug SS subsystem and look directly at those registers and say, oh, my RAT configuration itself is broken. Or maybe the GPIO registers are misconfigured for some reason. So this is an escape path that you have with the mem AP port. All right. Anyway, so the TCL option is also available where you can, like, for example, we had the gel scripts, right, with CCS. You have a network port here through which you can send automated TCL scripting. You can actually map this up with auto expect as well. There's something called expect scripting, which is interactive. So you could like literally write if conditions and a lot of other stuff that you could do with the TCL connection too. So there are so many different options with OpenOCD that you can do, literally. Many of these stuff is also enabled in different ways when you look at CCS or Lauterbach. They have their own scripting styles, which is very different from how OpenOCD does it. Anyway, going back here. So this is how we start up OpenOCD. Next thing that we want to look at is how do we debug U-Boot. So I picked 2 areas. Now, I picked U-Boot as one of the areas to look at. The other area that I picked is Linux to look at. In both these cases, I'm using A53 as an example, but it doesn't need to be A53, just a heads up. It could be R5 or it could have been M4. Just for ease of presentation, it is A53 right now. So I have built already OpenOCD, U-Boot, and I have installed the same U-Boot on the board. This is not TI U-Boot. but instead it is the very tip of the latest U-Boot out there, which is from U-Boot Master itself. And we are debugging RC4 version somehow. So all that is built, and all my stuff is in build folder under U-Boot. So if you look at U-Boot ARM v8, you'll see all these images available. Now, U-Boot has two stages of booting. One is, the first stage is where the U-Boot has not done a relocation of itself. Right now in the shell that you see here, it has already completed its relocation. Okay, so if you are debugging U-Boot prior to relocation, there is a slightly different step you have to follow versus the step you have to follow after the relocation is complete. Now, all this is part of the U-Boot documentation, so no big deal there. But this is something to be aware of. Otherwise, you'll be like, I loaded my symbols, but it doesn't show that, right? That's possible. So bd info, and if you run bd info, you will see something called as reloc address. This is the address to which U-Boot has relocated itself. And we use that when we load the symbols in. And we'll use this in a minute. So for debugging purposes, the debugger that I'm going to use as a initial start is going to be GDB. Okay, so there's something called a GDB multi-arch. GDB multi-arch. Now I can run this and it'll drop me into the GDB shell. The other option is to use EX, which would give me a list of commands that I can provide to GDB itself without having to type them in. So target, extended remote, localhost, Poland. Now, what do I want to debug? I'm going to debug 334. And I'm going to say that my set arch 64. I'm going to debug in ARM64 mode. Boom. It has already attached. Notice at this stage, you see this message that is coming out of OpenOCD that says current state is EL2H and the state has been halted. And this happens automatically. Right now, even if I press enter, nothing is going to happen on U-Boot because OpenOCD has taken control of the processor. The same thing is happening here. Okay, I got this wrong. My processor has kind of attached to the OpenOCD. Sorry, my GDB has attached to OpenOCD, which in turn has halted the processor right now. It shows which address it is halted at, but it doesn't show any trace. It doesn't know how to decode the stack dump either. And this interface, some people like this interface. I hate this interface. Everything is command line. You have to type, stack to see where this. Anyway, I'm no good at this using the command line interface for GDB. This is where I like using GDB dashboard. So I do source. Voila. So now GDB dashboard has shown me everything that I need to see, including how the text looked like, assembly in that view, everything that I like seeing in a debugger. It shows that right in front of me. Register dump, and if there is any decode that OpenOCD is able to do, it shows me that as well. It shows me where in assembly it is standing, and it shows me variables and stack all in one single screen. So I could do step, next, continue. Okay, Control C to stop again. Remember, I had hit a couple of enters here, which is paused. So when I hit continue, it goes. And when I hit Control C, it stops again. Now you will notice that it is trying to read the SPSR EL3 register, and it cannot. There is no way that when you're coming from the processor view and you are in EL2 world, exception level 2 world, you can't go into exception level 3 and read its register. For some reason, GDB dashboard is attempting to do that. There are a couple of patches to fix this in OpenOCD that have not been merged. They're in the review cycle. Once those get merged, hopefully this kind of warning will stop happening. So don't freak out when you see this. There is a meaning for it. Many of the debuggers try to dump all the registers that are possible within the processor and ignoring the exception levels. And OpenOCD comes back and says, I can't do that because you are on the wrong exception level. So lower the exception level, lower the privileges. So EL0 has least privilege compared to EL3. U-Boot runs in EL2. So you can debug everything EL2, EL1, and EL0, but you can't debug or look at the registers in EL3. And that's what is happening right now. So the next step after this is to load my symbols, right? So symbol, for that, I need to know where my ELF file is. CD build, CD U-Boot, CD RV8, real path U-Boot. So I'll make a mistake initially just to show you guys the mistake I'm doing. So typically we would just say symbol file and give him the actual symbol, right? You won't see anything. It still doesn't show you the text. And the reason for that is that the U-Boot has done a relocation. And if you remember previously, we had spoken about this reloc address, right? And that's the address that we need to use here. So again, for the sake of our sanity, this has been documented. When you come into the GDB side, it gives you that, and it tells you what to do. So the typical thing is to do add symbol file, ELF file, and the relocation address. So let me remove the old, yes, I don't want the old symbol file, and give the reloc address. Where are you? There you are. I'm messing something up here. Not able to remember. Add symbol file. That's the reason. My bad. Yes. Continue. Control C, and voila. Now it starts to show you exactly the stack trace on which function it is on. It tells you on which function the assembly is sticking at, etc. Now you can actually see the full view of the text. And this is key, because without this, you'll be sitting in debugging code, just looking at the assembly, which you can't make sense out of. So this is essentially how the GDB experience feels like. So you could do set step. After loading the symbol file, it will show you as it is stepping through the next level of steps. Oops. You could do finish, which will quit the session for me. Anyway, so this is one technique of doing debugging using GDB. Yes. The other way of doing GDB debug, which you would probably appreciate, would be to use VS Code. So I put a link here. So this is the link that I put on the PPT. By default, U-Boot source code doesn't have .vs code folder. Now, if it did have it, these are some of the extensions that will make your life easy. And here are some of the configurations that you can use automatically to see what we just saw with GDB, vanilla GDB. So I have done this, and this link is already available within the PowerPoint. So I've done that already. So go to U-Boot, code dot. All right, my friend, come back here. So it shows automatically. It gives you the VS Code option for tasks, JSON, etc. And if you pick on the debug and you select A53 debug, which is what my task list provides, it'll automatically attach and load it up here. So I had to give the text address difference, which I did not put in because I was debugging vim.vs code /launch JSON. And when you add your symbol files, you can actually tell him what the offset is. In this case, I gave 4300, but the actual reloc address is 47. That explains why. So going back into VS Code, let us stop this and disconnect. Try this again. There we go. So now you have capability to step into the source, step all the way through the source in VS Code itself. And you can see the call stacks on the side. There is memory view that you can pull up on the side, etc. So there are different schemes with which you could use. For folks who are using VS Code, right? This might be much more easier for you because you're using VS Code for programming, so you can do the debug as well within the same environment. But U-Boot source by default will not have the .vs code folder. The same thing appears even for Linux kernel. It doesn't have the .vs code folder either. But the same technique can be used for debugging Linux too. So 44. All right. So this is on, let me disconnect this guy, on the U-Boot debugging. So this is the different ways that you attach to the processor, you can debug it. But you also need some tricks to work with U-Boot efficiently. Now, these tricks are a little independent of whatever debugger that you're using. So one of the tricks that you have is that during the very early stages of boot, right? And this is the initialization stage, even you know, the ARM assembly stage of code. You may have to do some level of debug. In which case you want your entry point within start.s, the very first line of entry point of U-Boot, you want to put a debug there. The simplest way of doing that is to put a dead loop in start.s. Again, we have documented this as part of our U-Boot documentation. So if you go into the U-Boot documentation, you'll see these examples, how to do them. This is one way of doing it in start.s. The other is in board initf. Now, typically, this is the breakpoint that most of us typically will use. This breakpoint, essentially what you're doing is to set up an infinite while loop before any of your initialization code really runs. And when you put this, when you put a build of this in an SD card and you start your boot up, you'll see nothing. No prints will be visible, especially if you're debugging R5. Or if you're debugging the A53 SPL, you'll see the R5 debug prints appear, but nothing on the A53 side. Once you attach OpenOCD or any sort of debugger, you change this variable to 0, and you will exit this little hang loop that we have put in so that you can debug the rest of the code. Now, something to keep in mind, if you're working on AM64 or AM65, now this is an exception case. TIFS, actually J721E, let me rephrase this. If you're working on J721E or AM65, in both these cases, TIFS is actually loaded by the R5 bootloader, right? So ROM will wait up to 3 minutes for TIFS to get loaded. And if it doesn't get loaded within the first 3 minutes, it will automatically trigger a watchdog for you. So you want to be careful about that. There are some tricks with which you can control this by disabling the watchdog. But if you don't have the disabled watchdog trick in mind, then the only way that you can debug this is to do your entire debug within a period of 3 minutes. And we actually ran into this when we were debugging J721E U-Boot. Now for the rest of the devices, since we are using multi-certificate, ROM will automatically load TIFS firmware and the watchdog will be pet by TIFS itself. The other scenario that you have to be careful about is if you're debugging TIFS itself. Now, if you stop petting the watchdog is going to fire, right? And it's a windowed watchdog. So you have to be careful about when you're petting it. So the only way for you to debug TIFS is to actually disable its watchdog. That's the only way you'll be able to debug TIFS. And there are, again, some registers that you can configure to enable that work to do. But in most cases, for most of the U-Boot debuggers or Linux debuggers, you don't have to bother with that. Because the watchdog will be petted by TIFS and you can debug everything after within U-Boot. Right, so that was on U-Boot debugging. So two places to debug. One, if you want the very early part of U-Boot itself, you can debug it there. Or in most cases, you'll be debugging from boardinit.f. Now that doesn't mean that you have to use boardinit.f. If you have a fairly good idea where the failure is, you could add the same while one loop there and start debugging too. That's another option that you have. Right. So moving on. The next topic I wanted to show was kernel debugging. Now this is extremely touchy topic with people because people like to debug Linux kernel by, well, printf. You know, dev error, dev debug, whatever they like, right? That's usually the most preferred option in terms of debugging. Now, there are good and bad parts of it. Good is that you can iterate really fast. The bad part is every time you want to see the next level of debug, you have to add yet another printf and you have to iterate again. If you're using JTAG solution or if you're using KGDB, you can debug this using GDB interface. You have two options that is available. One is KGDB, other is using a JTAG debug. Now, the instructions that we have provided here is independent of what kind of debugger you're using. You can use CCS, you can use OpenOCD, or you can use Lauterback. You still have to do these two steps. There are two things that you have to literally disable in this case. There's something called as core site driver within Linux, and there is a core site PMU Arch system PMU control. Both these are enabled by default within ARMv8 kernels today. Unfortunately, OpenOCD or any JTAG tool needs to use core site to actually debug the processor. So if Linux is using core site, then the JTAG debugger will conflict with it. And you end up in a weird state as a result. Unfortunately, I haven't seen command line options for us to disable this at this point. So you have to literally disable it, in your .config, and you'll have to rebuild your kernel. The other three things that you want to be careful about, and we learned this the hard way, is that by default, Linux tries to protect itself. So it puts its MMU table in such a manner that where Linux functions, kernel functions or driver functions are, the text sections are read-only mode, which means that if you have to set a software breakpoint, you have to modify that source by adding an instruction in the middle. And Linux will not let you do that because the MMU table will protect itself. So you have to turn that off, which is what RO data equal to off does. The second thing you have to do is to switch off CPU idle. Now, typically, this is a don't care because we don't have any power state beyond WFI. We don't have, CSWR and OMAP style power states here. If you achieve such power states, the processor switches off itself, right? And CPU idle doesn't care whether you have a JTAG connected or not. It will go and try and attempt to achieve the lowest power state possible. So disable that guy. The third guy to disable is kernel address link randomization, KSLR. What that does is to take your take your functions where they were initially linked and jumble them up on every boot. So literally your symbol table is mixed up as the kernel is booting up. Now this is a security measure and it's enabled by default. But that doesn't work with a symbol table when you are trying to debug. So you have to disable KSLR as well. So once you have disabled this, your kernel is in a state where you can actually start debugging it. And I have already done that in the kernel that I'm about to boot up here. Okay. So
Sean, do you mind if I interrupt you for a second?
sure.
The other one that I've run into is perf events. So I've disabled perf events because the kernel will use hardware breakpoints for those, and it will wipe them all out. And
So
yeah, go ahead.
yeah, so the PMU perf is this is the option that I had to disable within the default def config. I didn't have to completely disable perf either.
Well, I think that it only shows up though if you set your initial while loop before perf events is
Ah,
set up,
okay,
right? If you set that out and perf events is done pretty early. So
okay,
probably you set your while loop after that and you never saw it. But if you're doing really early debugging, or debugging the early boot process, I've run into this problem too.
okay, okay. Okay, so that would be something to consider.
Sorry, just one other thing. RCU stalls
Oh,
would
yes.
probably.
So yeah, you won't face that. Solve that one. And I was about to pull up my, and this is the latest series of patches that I pointed out here in the PPT here. So by default, your Linux will start off on a single core. Now, U-Boot debugging is a no-brainer, right? It's a single core alone. In Linux, you have two stages. The first core starts up, and then starts up all the subsidiary cores out. When you start up the subsidiary cores and you attach only to one single core, there is something called as read copy update thread running in Linux. And what it does is to monitor various CPUs and see which of the CPUs might have stalled. So if you stop only one processor, the RCU monitoring is running on the other processors, which look at this processor CPU 0 and say, hey, CPU 0 is stalled. And it starts dumping stack all over the place. And it looks like your system has crashed. The solution for that is to run in SMP mode. And you can use SMP debug today, once these patches are merged, on K3 platform. And this is a very recent change that has happened. So the way to do that, unfortunately, is a little irritating. I couldn't find a better way, nor could the reviewers find a better way. You say two things essentially here. Let me copy paste this so that way. Hey, I don't know why copy paste is not working today.
But by the way, the other cheap and easy quick way is to run in no SMP mode, right? So if you want to simplify things and make it very, 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 simple, kind of like a U-Boot environment, there's a no SMP kernel command line parameter that you can pass.
So in SMP mode, and this is something I've done so that you can now add operating system awareness to OpenOCD as well. So you can say, this processor is running Zephyr, this one, so other processors is running FreeRTOS, and all my CPUs of A53s are running in SMP mode. I can do that too. Now, to do that, you set the RTOS of A53 0. Two things that you do. You set V8 SMP debug equal to 1, and you set A53 0 into hardware thread mode. Now, hardware thread is a special OpenOCD concept. It kind of emulates GDB, like glibc threads. Each of the CPU will be emulated as a hardware thread. There's something called a Linux awareness too. If you're running in no SMP mode, you can enable Linux as the operating system, and Linux awareness will be available within OpenOCD. So that's another technique. But for us right now, we're going to use this. So let me shut this thing off. It's running. Okay, now one thing that you'll immediately notice, right, is that when I ran it previously, you saw that all the CPUs were visible. Okay. Now, okay, this I know. When I ran it now, you only see A530, only one A530. You don't see the rest of the A53s because all these 4 processors are now coalesced into a single CPU, which is what GDB exposes us. Now, give me 1 second while I work around a little bug in our system. Right, that's my editor. So upstream U-Boot tries to boot out of eMMC all the time, which is not what I wanted to do. Select 4. So kernel is starting to boot up. Okay, it's doing its user space stuff. And OpenOCD is ready to go here. And we do the same thing. Multi-arch minus EX target extended remote. Local host colon 1234 blank. Now I have attached to the A53s. Now, if you notice, all my A53s have stopped simultaneously. So I can run info threads and it'll tell me the location of each of my CPUs. Now I can load my GDB dashboard as well. Ta-dang. And it'll show me each of the threads that are available too, if you notice here. Doesn't show me the functions yet because I have not loaded the symbol tables yet. So let's do that. Of course, my SDSC I had to crash. But you can see this available as well. Now that I've loaded my symbol table, it shows up everything properly. It shows you your registers, it shows you where the code is, it shows you the breakpoints that are available, etc. Each of the CPUs. Now you can single step them through and you can see the next level, etc., etc., etc. Now we are actually sitting and debugging CPU idle. But in this state, I'm debugging all 4 CPUs simultaneously. I can switch threads and set breakpoints on whatever function that I want. All that is possible as well. Now, this is the kernel debugging technique. Now, you can also use VS Code for doing the same thing, similar to what I showed with U-Boot. The last topic is a little more trickier, which is you can essentially boot up on A53, run OpenOCD on A53, and start debugging your microcontrollers too. That way, you can do your development of on your VS Code on your PC, attached to OpenOCD that is running on the A53 on AM625, and you're doing development for the M4F or R5 without using anything, no JTAG cable or debugger of any sort. That is the last self-hosted debug stuff, but I think we are a little too late for covering that.